All right. So yeah, good evening, everyone. So this is gonna be a very delayed video, but oh well. I'll just try to get it finished tonight. This is going to be for the polynomial equations math written work. That's this one's written work four. Yeah, it happens on Tuesday, so I need to catch up. So let's start. So solving polynomial equations. First and foremost, I'd say the thing we need to do is to first differentiate what's an equation versus expression. So an expression is is simply like just this one where there's no equal sign. It's only used to evaluate. So like when you are usually in expressions, you're just asked to evaluate it. Like, what if x is equal to 4? Then what is the value of this one? But that's not our main gist. So the reason why it's called expression, it's just to express like a function or like that can be any value. And all you can do is really evaluate it. But for an equation here, as you could see, you have an equals 0 at the end. This equals 0, you can factor this one out. That we can factor this one out to find the solutions to what will make this 0. And we'll learn that later on. So you can find the roots in an equation but not in an expression. And then there's I think these are the two most used theorems. The fundamental theorem of algebra, it's basically polynomial with the degree n, where n is the highest degree, has n amount of roots. So this will help us figure out how many roots do we have in a polynomial. And secondly, we have the rational root theorem. So the rational root theorem is the factors of the last term over the factors of the first term. So we just need to add all of those possibilities. So let's try this with our example. So fundamental theorem of algebra. So by doing the degree n, so therefore we have 3 roots. So fundamental theorem of algebra, FTA. So that's 3 roots. So how can we apply the RRT, or the rational root theorem? So we need to find the factors of 24. So that's plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12, and plus minus 24. And then since the factors of the first term is just 1, we can just over 1, we can just cancel that out because yeah, this is the list of terms. Now as you could see, we can already eliminate an option here, and which is plus minus 5. So it's not this or that, because by RRT, as you could see, it's not listed here because 5 is not a factor of 24. So we can eliminate those. Okay, what can we do? So we can try to apply another theorem. It's called the upper lower bound. So it's an upper bound if okay, I'll use an example. So let's try to use number 4. Let's try to use positive 4 as a example here. So we put 4 over here, and we're gonna try to use synthetic division to divide it. So 1, 6, negative 4, and negative 24. And then we try this. So 1, bring this down 1. 1 times 4 is 4. 6 plus 4 is 10. 10 times 4 is 40. Negative 4 plus 40 is 36. 36 times 4 is 144. And this one is 120. So as you could see, look at this. Number 4, right? Number 4 is remainder 120. And think about it. Like, if we make the number 4 higher, what do you think will happen to this remainder? It will just become higher. So this thing is called, number 4 could be our first upper bound. So it's an upper bound if it's all positive also and with remainder. So these are, once you do before you set this number as an upper bound, obviously it has to be a positive in number, and then it also has to have a remainder. If it's zero remainder, that's a root and it cannot be used as an upper bound. Now I'm gonna show you an example of a lower bound. So kahit hindi naman siya sa even if it's not in the choices, let's try to I just want to demonstrate. Let's try negative 12 as our lower bound. So let's say you weren't given these choices talaga. Okay, let's just assume. So we put the same numbers, 1, 6, negative 4, and negative 24. And then let's try it again. So 1 times negative 12, negative 12. Then this is equal to 6. 6 times negative 12 is negative 72. When we add this, it's going to be negative 76. Negative 76 times negative 12, as you could see, it's going to be too high. But actually, negative 12 is not a lower bound here because it's not alternating. We'll encounter this later, but for lower bound, it must be alternating sign. And obviously with remainder. So our upper bound can be 4. So since we established number 4 as our upper bound, so obviously 4 is not a bound and 6 is not. Obviously, since 4 isn't gonna work, 6 is also not gonna work. So we can try something lower. Let's try 2. So if we do 2, we get 1, 6, negative 4, negative 24. And that's 1, drop down 1, 2, 8, 16, 12, 24, 0. So therefore, x can equal to 2. So therefore, one of the factors is x minus 2. Because why? 2, you can factor it in, it's 0. So let's try to build it up. Let's try to use negative 2. Negative 2. So that's going to be 1, 6, negative 4, negative 24. 1 times negative 2, negative 2. 4 times negative 2, negative 8. Negative 12. Negative 12 times 2, 24. 0. So as you can see, 0 again. So you can either solve for this manually, right? Or going back. So we know that x minus 2, right, is a factor. And this we can translate it into a quadratic expression. So it's going to be x squared plus 8x plus 12. So this is actually factorable because we have two numbers that product is 12 and the sum is 8, which is x plus 6 and x plus 2. So therefore, when we factor it, it's like this. So therefore, our roots are x is equal to 2, negative 6, and 2, negative 2. The reason why, we can also apply the zero product property. Because one of these, if they're equal to 0, everything else will be equal to 0. So that's basically the zero product property. So we've done the upper bound of FRT. So that's really it for the FRT. Multiplicity of roots, not yet. Zero product property and the rational root theorem. So I'm gonna pull up another example so that we can we can have the other theorems. Okay, so I found another example that we can use the upper bound, lower bound theorems. So first and foremost, let's use our FTA to know that there are 4 roots. Then by RRT, we can just list the factors of 16 because our first term naman is just 1. So remember to consider plus minus. So it's plus minus 1, plus minus 2, plus minus 3, no, not plus minus 3, plus minus 4, plus minus 8, and plus minus 16. Okay, so let's lay them out into a list from least to greatest. So it's negative 16, negative 8, negative 4, negative 2, negative 1, 1, 2, 4, 8, 16. So let's try to look for an upper bound first. So upper bound, let's try to use number 8. So, you know what? Let's try number 4 first. Number 4. So, number 4. So, oh wait. No, let's try number 8 talaga. Okay, number 8. So, let's list number negative 8, 1, negative 8, 24, negative 32, 16. So by doing synthetic division, we pull down 1. 1 times 8 is 8. So this becomes 0. 0 times 8 is 0. 24 plus 0, 24. 24 times 8 is 192. And when we add this is 160. 160 times 8 is 1,280. And then this ends up with 1,296. Now by logic, if 8 results in this very large remainder, what happens if we use 16? Obviously, that will get you further away from 0 remainder. So we can eliminate this as well, this first. So this is an upper bound because all are positive. And there's remainder. All terms are positive and there's remainder. How about for lower bound? Let's try negative 1. So let's see if we can eliminate all the negative roots. So, it becomes 1, negative 8, 24, negative 32, 16. So we just copy that. 1. 1 times negative 1, negative 1. Negative 8 plus negative 1, negative 9. Negative 9 times negative 1, that's 9. 24 plus 9 is 33. 33 times negative 1 is negative 33. Negative 32 plus negative 33, negative 65. Negative 65 times negative 1 is 65. 16 plus 65 is 81. So as you could see here, negative 1 pa lang, it becomes 81. What do you think happens if it becomes negative 2, negative 4, negative 8? It's only gonna get us farther again from 0. Now I want you to realize this. As you could see, it's positive, negative, positive, negative. And 0 can be used as a joker depending on the situation. It can be positive or negative. But in this case, it's very prominent that it's alternating sign. So that can be used as our lower bound. So because we managed to eliminate all of the negatives, we're only left with 3 roots. So let's try 3 roots is a small enough number that we can just manually solve for it. So let's try. So let's first try doing 1. So 1, negative 8, 24, negative 32, 16. And then we do drop 1. 1 times 1 1, negative 7. Negative 7 times 1, negative 7. Negative 24 plus negative 7, that's 17. 17 times 1, 17. negative 32 plus 17, negative 15. And negative 15 times 1 is negative 15. And we have a remainder of 1. So 1 is not a root. So how about number 2? So let's try to do this. 1, negative 8, 24, negative 32, 16. We'll pull it down. This is equal to 1. 1 times 2, 2. Negative 8 plus 2 is 6. Negative 6, sorry. Negative 6 times 12 is negative 12. That's equal to 12 when you add it. 12 times 2, 24. That's equal to negative 8. Negative 8 times 2 is negative 16, 0. So 2 is a root. But as you could see over here, we actually eliminated almost all the roots, pero we only have 1. Pero let's just make sure that 4 isn't a root. So 4, we get 1, negative 8, 24, negative 32, and then 16. Try again. 1, 4, then it becomes negative 4, then negative 16. 24 times minus negative 16 plus negative 16 is 8. 8 times 4 is 32. But this is 0. 0 times 4 is 0. And then 16. So 4 is not a root. We only have 2. What happens now? We only have 1 root. Sometimes roots can be repeating, such as this case. So what you want to do, since we have a sole root over here, we just continue our synthetic division with this one. So let's put number 2 again here. So we drag down 1. 1 times 2 is 2. Negative 6 plus 2 is 4. 4 times 2 is 8. 12 plus 8 is... Wait. Oh, sorry. 1 times 2 is 2. Then this is negative 4. Sorry. Negative 4 times 2 is negative 8. Negative 8. 12 plus negative 8 is 4. 4 times 2 is 8. Once again, we have 0. But let's keep continuing. Put another 2 over here. So, we do it again. 1 times 2 is 2. Negative 4 plus 2 is negative 2. Negative 2 times 2 is negative 4. 0. And then, as you can see, we keep reducing it until we have this expression, x minus 2. So that's equal to 0. So therefore, x equals 2. So we have, so this is, as you can see, this is 1, 2, 3, 4. Apat. So we're going to list that down as x is equal to, or e, 2 multiplicity 2 of multiplicity 4. And that's when you know if it's sometimes you use all the theorems and then it hasn't resulted in a favorable result. So all we need to do now is do the irrational and imaginary roots. So let me get another example or 2 more examples to cover that. Okay, so I have another example here. So let's try to use the polynomial equation x raised to 4 minus x raised to 3 minus 15x squared plus 3x plus 36. So by FRT, we have 4 roots. By RRT, we have plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18, plus minus 36. So in this case, let's try to narrow down the roots, or let's try to find the roots first. So let's try to define our upper bound. So let's try to use 6 as an upper bound first. So we can do 1, negative 1, negative 1, negative 15, 3, 36. Is that okay? Yeah. Then 1 times 6, 6. Negative 1 plus 6, 5. 5 times 6, 30. This is just 15. 15 times 6 is 90. This becomes 93. 93 times 6 is 558. And this equals to I don't have my calculator with me right now. 4 carry 1, 594. So as you could see, it's all positive, and we have this one, another what do you call this, remainder. So 6 is upper bound. So let's try naman 4. Since obviously none of these will work, so the positive won't work. So let's try number 4. 4, and then we use 1, negative 1, negative 15, 3, 36. And then we can just use 1 times 4, 4. This is negative 3, negative 12, negative 27, wait, negative 108. This becomes negative 105. Hold on. Oh, this becomes 3. So yeah, 3, sorry. 12, and this one becomes negative 3. Negative 3 times 4, negative 12. Then this one becomes negative 9. Okay, there. Then this one becomes negative 36. So this is 0. So therefore, this is a root. Now, we can just use this smaller expression to find the other roots. Let's try to use negative 3. Let's try to use negative 3. So, when you use negative 3, 1 times negative 3 is negative 3. This becomes 0. 0 times negative 3 is 0. This becomes negative 3. And then this one becomes 9. 0. Okay, may quadratic na tayo. We have a quadratic already. So, let's use the zero product property to build our polynomial. So, since we know that 4 is a root, therefore, x minus 4. Because 4 minus 4 is 0. Then we also know negative 3 is a root, so we also know x plus 3 is 0. And then lastly, this is x squared minus 3. So let's just list that down. As you could see, we know that x is equal to 4, negative 3, and we have x squared minus 3. If we do x squared equals 3, therefore we square root both sides. So x squared is equal to 3, right? Then x is equal to square root of 3. But this is where a theorem comes in. This is called quadratic surd theorem. That these root pairs, right? This root always come in positive negatives. So we can put negative root 3 as well as root 3 itself because quadratic surd. And that's also known as the irrational root theorem. I think so, but like that's the name I come up with. Okay, very nice. But let's say what happens if we have something like this. Let's try to use a different equation. Actually, almost the same equation. In fact, what happens naman if this one becomes, say for example, we have x minus 4, x plus 3, and then x squared plus 9. So obviously, x is equal to 4 and negative 3 once again. So very simple, right? We can just equate it. So very simple, right? To find the 0 of this one, we can just equate it. X squared plus 9. We move it to the other side. X squared equals negative 9. But hold on. You cannot multiply two numbers together, two identical numbers together, and result in a negative. Even negative times negative is positive. So what's the answer now? The answer is just the imaginary unit. So let's still square both sides. So x is equal to negative 3 square root of negative 3. Sorry. Yeah, we square both sides. Yeah. We square both sides to get x is equal to 3i or negative 3i or 3i. Or you could also rewrite this as root of negative 3 and negative root of negative 3. So why is this the case? Because all you need to do is actually find the square root of this one, and then that's basically it. So basically that. So just square root this number and then find the plus minus. So in this case it's negative 9, right? So it's just negative 3i and then 3i. Once again, similarly for the complex numbers, this is what you call the complex conjugate. Basically, if you have 3i as a root, it also means that its negative counterpart is also a root. Similarly, for more complex ones, such as 4 minus 6i, if 4 minus 6i is a root, 4 plus 6i is also a root. So these are complex conjugate theorem. Yeah, similar here. If 3 plus square root of 3 over 2 is a root, therefore 3 minus square root of 3 is also over 2 is also a root. That's also what you call quadratic surd. And that's all what you really need to know. It's basically the same thing over and over again, but we learn cases and ways how to solve them more efficiently over time. So once again, it's 12. Once again, thank you very much for watching and listening to the end. It's 12:30, and VM week drained all my energy. Hope you had fun in Vision Mission Week to my fellow schoolmates out there. And if you're not, well, hopefully you guys have your own foundation week so that you guys also had fun. Okay, guys, it's 12:30 a.m. Make sure to sleep well tonight. Get a rest this weekend. For all my schoolmates out there, we have no school on Monday. You can use that time to watch this video. And once again, take care of yourselves, guys. And I'll see you guys in the next one. Bye.